Okay, good morning, ladies and gentlemen. Hope you're having a nice day on this eve of the AB calculus exam. In this video, we're going to go over the AB1, part C, D, and E, and AB2, part D. These were the only parts that I saw asked about in the question stream. Of course, if there's another part that you'd like to go over with me, stop by SGI or email me or something like that, and I'm happy to help. All right, but let's start with part C. And I will say that this question is, in my opinion, a little bit contrived. I think it was sort of purposely made like very complicated. But anyway, let's go through it step by step because these are all concepts that are important. And I think that's what the creator of this problem was trying to do, just make a problem that forces the student to go through a lot of different concepts. So in that sense, whoever made this did a very good job of doing that. So we have a function and we are given the information that this limit can be evaluated using L'Hopital's rule. What does that mean exactly? Well, if a function's limit at a certain point can be evaluated using L'Hopital's rule, then that means with direct substitution, the limit is either going, is either approaching 0 over 0 or plus or minus infinity over plus or minus infinity. In other words, this means that if you have a fraction and you use direct substitution, you're getting some sort of indeterminate form. All right, so the fact that the limit as x approaches 3 of k of x can be evaluated using L'Hopital's rule, well, that tells us right off the bat that when we use direct substitution of 3 into this function, both the numerator and the denominator, we are either getting 0 over 0 or plus minus infinity over plus or minus infinity. Now, if you just take a look at the graph of f prime, and if you take a look at the expressions that you're given in both the numerator and the denominator, it's pretty clear that both of these are finite values when you plug 3 in. And so what that means is we're probably, in fact, it means we're not dealing with the case where the numerator and denominator are some sort of infinity. Instead, we're dealing with the case where both the numerator and the denominator are equal to 0 when we substitute 3. All right, so right off the bat, going through that logic, this implies that k of 3 must equal 0 over 0. All right. How are we going to use that information? Well, the first part of the problem tells us to find f of 3. And if you look at the denominator, there is an f of x function, and it just so happens that when we plug 3 into x, that gives us f of 3. We also know that the denominator is equal to 0 when we substitute 3 in for x. So we have the expression that says 3 times e to the 2 times f of 3 plus 5 minus 0 is equal to 0. And why did I say minus 0? I meant minus 3. Minus 3, right? Because I'm substituting 3 in for x. So we have this equation. And now I'm just simply going to solve for this guy right here. This is what I'm interested in finding. All right, so I'll add 3 to both sides and then divide by 3. So I'll have e to the 2 times f of 3 plus 5 is equal to 1. Of course, to get rid of the exponent, the base e, I need to apply ln to both sides. So applying ln to both sides, I have 2 times f of 3 plus 5 is equal to ln of 1. Well, ln of 1 is 0. All right, and now solving for f of 3, you see that f of 3 is equal to negative 5 over 2. Okay, so that solves the first part of the problem. The second part of part C says to evaluate this limit. All right, well, the limit as x approaches 3 of k of x, we have already determined is equal to 0 over 0. So what I must do is apply L'Hopital's rule to then evaluate this, this limit. L'Hopital's rule says that I take the numerator and find its derivative. Then I'll take the denominator, find its derivative, and then just simply find the limit of those two, the ratio of those two derivatives. So let me just rewrite the expression down here. Minus 4x over, what is it, 3e to the 2f of x. Oops. Now, to take the derivative of the denominator, so the derivative of the, I'm sorry, let's start with the numerator, of course. Take the derivative of the numerator with respect to x. So that's d dx of 3 times the integral of 4 to 3x of f prime of t dt minus 4x. First, what I'm going to do is evaluate that definite integral using the fundamental theorem of calculus part 1. That would give me f of 3x minus f of 4. And then still we have that minus 4x inside the parentheses. And now I can apply d dx here. So I have 3 times the derivative of f of 3x would be f prime of 3x times 3. That's the chain rule. The derivative of f of 4 with respect to x is just 0. And the derivative of 4x with respect to x is just 4. So this is your numerator's derivative. Okay, so we'll set that aside for a moment. This will come into play in just a moment. Now let's get the denominator and find its derivative. D dx of 3e to the 2 f of x plus 5 minus x. Oops, that's a 1. All right. So the derivative of this first term, e to the f of 2 times f of x plus 5, that's a composite function, so I'm going to need to use the chain rule. So you would get the derivative of the outer evaluated at the inner times the derivative of the inner. So the derivative of 2 times f of x plus 5 is just 2 times f prime of x. All right, and then you have the derivative of x, which is just 1. All right, so here's the derivative of the denominator. And now let's find the limit. So L'Hopital's rule says the limit as x approaches 3 of k of x. If that approaches 0 over 0, then I can differentiate both the numerator and the denominator and find the limit of those, the ratio of those derivatives. So I have 3 times f prime of 3x times 3 minus 4 all over 3 times e to the 2 times f of x plus 5 times 2 times f prime of x, all that minus 1. All right. Now it's just a matter of direct substitution. So here we have a 3 times 3, which is 9, times, when I substitute 3 in for x, I get f prime of 9 minus 4. So that's going to be my numerator. My denominator, here this 3 times 2 is 6, times e to the 2 times f of 3 plus 5 times f prime of 3 and minus 1. So now it's just a matter of me going about evaluating. All right, so this limit is going to equal 9 times, well, what's f prime of 9? Well, I have the graph here of f prime. F prime of 9 is right over here. We were actually told, actually, I guess we're not really told that explicitly, but I think it's pretty clear to see that when x equals 9, f prime of 9 is equal to 0. So we have 9 times 0 minus 4 in that numerator. And then we have 6 times e to the 2 times f of 3. Well, that's actually what we just found up here in the first part of this problem. F of 3 is negative 5 over 2. So we have 2 times negative 5 over 2, that quantity plus 5, times f prime of 3. Again, I'm going to go up to the derivative graph, and we're told that when x equals 3, f prime is equal to 3.5. And all of that minus 1. All right, so we have a negative 4 in the numerator. And let's see. 6 times 3.5, I believe, is 21, times e to the 2 times negative 5 over 2. Oh, wow, this works out nicely. 2 times negative 5 over 2, of course, is negative 5. Negative 5 plus 5 is 0. And then we have minus 1. So we end up with, and of course, e to the 0 is just 1. So we have negative 4 over 20, which is equal to negative 1 over 5. And that should be your limit. Okay, so a lot of work to finish part C. I'm going to pause here for a moment just to let you, think about it for a little bit. And I'll be back in just a moment. All right, welcome back. On to part D. So part D gives us this differential equation, and we're actually asked to find the second derivative. So we're just going to apply d dx to both sides. Just a little rundown of what other information you're given. You're told that y is equal to h of x. In other words, y is some implied function of x. So wherever you see y here, this is actually a function of x, which means we're going to need to use implicit differentiation. We're also told that h of 1 is equal to 2. Okay, that might come in handy in a bit. And we're told that, or really the whole goal of the problem is to determine, is h of 1 increasing or decreasing? All right, so of course, sorry, 1 second. I just want to make sure that that's actually what they're asking. 1 second. All right, so I'm glad I checked because I was mistaken. They're actually asking, is H1 concave up or concave down? And that makes more sense because they're asking for the second derivative. So the second derivative is exactly the tool that we use to determine concavity at any given point of a function. All right, so anyway, let's get into it. Let's apply d dx to both sides. Okay, the left side, very simple, just becomes d squared y over dx squared. The right side, a little bit more complicated because, well, there's a product of two functions, so we need to use the product rule. So I like to do it the first function times the derivative of the second function. The derivative of the second function is just 3 dy dx. Plus the second function times the derivative of the first function. That is itself a composition, so the derivative of that first function is f double prime of 2x times 2. So that times 2 is because we're taking the derivative of 2x and multiplying by that derivative, because the chain rule says that that's what we should do. So this is the second derivative. Let's see if we can simplify a little bit. So we don't want dy dx here. We actually want to replace it with this guy right here. So let's do that. So d squared y over dx squared is equal to f prime of 2x times 3. Now we have the original function, which is f prime of 2x times 3y minus 1 plus 3y minus 1 times f double prime of 2x times 2. All right. And now all we have to do is plug in x equals 1. Sounds simple. There are going to be like a little tricky things along the way, but let's just do that. So we're going to plug in x equals 1. So that gives us f prime of 2 times 3 times f prime of 2 times, all right, so we have 3y, but remember y is equal to h of x, right, as we see here. And so when we're plugging 1 in for x, we have h of 1, and we're told that h of 1 is equal to 2. So that's where that information comes in. So we have 3 times 2 minus 1 plus, same thing, 3 times 2 minus 1 times f double prime of 2 times 2. All right, so we have to evaluate this whole thing. And keep in mind, though, that really all we're interested in is whether it's positive or negative. That will tell us enough about concavity. So f prime of 2, let's go up to our derivative graph. F prime of 2 is equal to 5. There's going to be a lot of scrolling up and down here. So we have 5 times 3 times, well, f prime of 2, again, is still 5, times 6 minus 1 is 5, plus 6 minus 1 is 5. All right, f double prime of 2. Let's see. As you can see, well, f double prime is referring to, if this is the graph of f prime, then f double prime is the slope of the tangent line. And the slope of the tangent line at x equals 2 is 0. So f double prime of 2 is 0. All right, but really the big payoff here is that you can see that this is definitely a positive number, and therefore we can say that h of 1 is concave up because d squared y over dx squared is positive at x equals 1. All right, there we have it. Again, take a moment to think about it. I'm going to pause just to, it looks like we need a little bit more space, so I need to adjust some things for going over part F or E. Yeah, I think we're going over E. All right, I'll be back. All right, welcome to part E. Part E gives us or asks us to determine on some interval, which is between x equals -1 and 5, when is this function h of x increasing? Now, of course, to determine if a function is increasing, we need to look to its derivative, okay? And it just so happens we were given the derivative function, right? dy dx is the same thing as saying dh of x dx, right? So this is this is h prime of x. All right, so we're going to analyze this and determine when is h prime of x positive. That will tell us when h of x is increasing. One piece of information that from part D that might have seemed like sort of like throwaway info is the fact that they're telling you that y is greater than 1/3. This is extremely important in analyzing this derivative function for being positive or negative. Well, because let's see why. So if y is always greater than 1/3, then think about this expression over here, 3y minus 1. If y is greater than 1/3, that means that 3y minus 1 must be greater than 0. All right, and why is that important? Well, this derivative function is f prime of 2x times this value here. So when we multiply two numbers, you know, if we have a positive times a positive, then we know that that product is positive. So that being said, since we know this term must be positive, this means that the derivative dy dx must be positive whenever f prime of 2x is positive. So really, this boils down to when is f prime of 2x, when is f prime of 2x greater than 0? All right, let's see if we can figure that out. So I'm first going to analyze f prime of x between -1 and 5, and then we'll kind of convert to 2x in a moment. So here's the graph of f prime. We see that f prime of x is equal to 0 when x equals 0, 4, 6, and 9. So let me go ahead and write those things down. 0, 4, 6, 9. This is when f prime of x is 0. Oop, but we're only focusing between 0 and 5. So actually, I mean -1 and 5, sorry. So we only have zeros at x equals 0 and x equals 4. But what's happening between those numbers? Well, we see that from -1 to 0, the derivative f prime is negative. Okay, from 0 to 4, f prime this whole time is positive. And then from 4 to 5, we see negative. All right, so we see that f prime of x is positive on x equals 0 to x equals 4. Okay, but what does this mean for f prime of 2x? So just give me one moment. All right, welcome back. I just wanted to fill you in on a correction that I made. I realized that when we are on this interval from -1 to 5, that's with respect to h of x. And so right now, since I'm analyzing f or f prime really, I'm going to look at f prime on its entire interval from -2 to 10, and then that entire interval will be required when we analyze h of x from -1 to 5, and you'll see what I mean. So basically, we have found the following, that f prime of x is positive from 0 to 4, and also from 6 to 10. So we can set up the following intervals. We know that with x between 0 and 4, we have f prime being positive. And with x between 6 and 10, we have f prime of x being positive. This can equivalently be written in terms of 2x. So it's sort of like a substitution. Instead of using the variable x, we're using the variable 2x. I would have preferred to use maybe different letters here in this problem, but just understand that this is like saying u is equal to 2x, and over here that this is the letter u, or something like that. So this is just a substitution of the variable x, and we're substituting, instead of using x, we're using some other variable, which is called 2x. All right, so instead of x, I'm going to use 2x, and I still have these two intervals. Okay, and now to get these intervals simplified to be in terms of x, this becomes 0. So I'm dividing both sides of this inequality, or let's say all sides of this inequality, by 2. So I get the interval between 0, x, and 2. Similarly over here, I get between 3, x, and 5. So basically what we're seeing is that h of x is going to be increasing Now this is starting to get a little bit messy. H of x is increasing when f prime of 2x is greater than 0. And as we discovered down here, f prime of 2x is greater than 0 when x is between 0 and 2. So I'll say this occurs when x is between 0 and 2, and when x is between 3 and 5. Okay, all right, I'm gonna actually stop this video and create an entire new video for part D. Actually, since it's one part now, I'll add it to the end here. Of course, you could always watch at double time. So let me pause and set up the next question. All right, here we go with part D. Okay, part D. So with this problem, we're dealing with sort of a pizza delivery situation. Okay, part D goes ahead and introduces this function which models the number of calls. All right, so at any given time, we can determine the number of calls based on this function, but actually we also see that this function can be expressed in terms of the number of drivers. All right, so there's a few things that occur. There is, you can see later on they ask about with respect to time. So big F is a function of delivery drivers, but it's also a function of time, right? As time changes, the number of calls also changes. Similarly, this function x, which, or let me circle this one, which represents the number of delivery drivers at any point in time, this is itself a function of time, right? So we have to keep in mind that both of these functions are implied functions of time, as well as being related to one another, okay? This information here that says when there are 60 drivers, the number of drivers is decreasing at a rate of 7/24 drivers per hour. So I've converted that information to mathematical symbols. So when x of t is equal to 60, x prime of t is equal to, actually should be a negative over here, x prime of t is equal to negative 7/24 drivers per hour. So when they say number of drivers is decreasing at a rate, they're referring to a derivative, right? So that's x prime of t. All right, so now that we understand the symbols, let's go ahead and answer the question. According to this model, what is the rate of change of total delivery calls with respect to time in hundreds of pizzas per hour at the time when there are 60 drivers delivering pizzas? All right, long story short, we're wondering what is f prime of x at x equals 60? All right, well, we need to differentiate. And I'm going to use, the one thing is you have to pay attention that we are looking at the derivative with respect, the derivative of big F with respect to time. So I'm applying really d dt to both sides of this equation. And which means that in this instance, I'm thinking of x not as x, but as x of t, or some function of time. So I'm going to need to use the chain rule whenever there's a composition. So x of t squared, for example, is a composition. All right, so a lot of things going on here. There's going to be a chain rule, but first and foremost, there's the quotient rule. So with the quotient rule, I do the bottom function times the derivative of the top function. That top function's derivative is going to be 2 times x prime. Again, we're differentiating with respect to time. So that inner function has a derivative of x prime of t. Okay, so I do bottom times the derivative of the top minus the top function times the derivative of the bottom. Derivative of 200 with respect to time is 0. The derivative of negative 2x with respect to time is negative 2x prime. All right, and then we do all over the bottom squared. All right, well, we know that x is equal to 60 in this situation. So let's go ahead and fill in that information. So I have 200 minus 2 times 60. I could drop the function notation just to make things a little bit more simple. 200 minus 2 times 60 times 2 times 60. Now, the tricky thing is I need to know what x prime is at this particular moment in time. Well, we were given the information that when x is equal to 60, x prime is negative 7/24. So I'll just plug that information in there. Minus 60 squared times negative 2 times negative 7/24. All of this divided by 200 minus 2 times 60, and that entire quantity squared. F prime of 60. All right, I'm going to take a moment and calculate this number. All right, welcome back. Simplifying, you should get negative 49 over 64. Of course, let's add the appropriate units. So F is time. Total delivery calls. So hundreds of pizzas per hour. What would the, okay. Negative 49 over 64, hundreds of calls per hour. All right, so at that instant, the number of pizza delivery calls in hundreds of, actually, I think it's pizzas per hour, is decreasing at that rate. Okay, ladies and gentlemen, this was a very long video. I'm going to stop it now, and I will be creating one more video which goes over the other 2020 mock exam problem from the College Board. All right, I will see you then. Take care. Bye.